Okay, so in this video we're going to start our next unit, which is over circuits, which is a really interesting unit because circuits, in today's age of electronics and computers and smartphones and whatnot, circuits are around us all the time. And so, just some examples of circuits you use or experience every day. We can just name a few. Obviously, the outlets in your house. Every time you plug something into a wall and get power from that, you're basically creating a circuit. And so your house or your apartment has wires inside the walls that basically constitute a giant electric circuit. Your computers use circuits. Smartphones, okay, so your phone, your TV, basically any electronic device has some type of circuitry built in. Okay, and so circuits are something that appear all around us. Now, we're not going to, go into super detail about the different types of circuits. We're mostly going to stick to the basics. But electronics and the concept of the electric circuit is really useful to understand just the basic principles, since these are things that are around us all the time that we use. When we turn the light on, we're making a circuit, right? When we plug in the toaster to make toast, we're creating a circuit. And so we're going to start off by talking about, what is the circuit and what are the elements what are the key elements you have to have in order to construct an electric circuit. Okay, so pause it here if you need to. I'm just going to erase this. Okay, and so the first slide of notes, okay, right here, talks about the elements of a circuit. Okay, now right off the bat, before we get to the elements that make up a circuit, you have to know that a circuit basically works by moving electrons, that is, particles that have charge, around in a closed path. Okay, and we'll see that in a second when we look at a simulation. But that's basically what a circuit does. It transports electrons, in some type of path. Now, the key elements that all circuits have to have, you have to have some type of conducting material. Okay, conductors. An example of a conducting material would be like a metal. Okay, so conducting material could be like a wire or piece of metal filament and like a light bulb. A very common type of conducting material is copper. So a lot of you have copper wires, in your homes, powering your outlets or your internet, your cable, stuff like that. Okay, so metals are the most common type of conducting material. So all electrical circuits have to have some type of conducting material. You have to have a closed conducting path. And by closed, basically, I mean, you have to be able to make a complete loop without any breaks in order to have a circuit. The reason is, the way a circuit works is, like I said, by moving an electron around in a closed path. And I'll show you what that looks like later. But it does have to be a closed path. There can't be any openings in the path. So, for example, if you're looking at a basic circuit and you cut the wire with scissors, if you break that path, then you stop the circuit from working. Okay. Now, of course, you shouldn't be cutting any wires with scissors. That's dangerous. But it's just an example. And you also have the third element you have to have for a circuit is what's called a voltage source. Okay, we'll talk more about voltage, what voltage is here in just a minute, but you have to have some type of voltage source, something that's providing power to the circuit. Okay, so let me just show you a simulation, okay, constructing basic circuits. So let's say I gave you, a battery and some wire, and I told you to make a circuit. Okay, so here's my little battery, my simulation battery, and let's say I take some pieces of wire, and I attach them to the end of the battery. Notice right now, nothing is happening, and the reason nothing is happening is because I don't have a closed conducting path. The blue dots in the simulation represent the electrons. Okay, now even though they're attached to a battery, they have no place to go because there's this giant opening right here between the wires. Okay, so I don't have a closed conducting path, so I don't have a circuit. If I take this piece of wire here and I attach it to the ends, watch what happens. Okay, so now I have a circuit. Notice that the battery is actually on fire, which is bad, and it says animation speed limit reached. This is a circuit, but this is not the type of circuit you want to make. Okay, this is actually what's called a short circuit. You might have heard the term short circuit before. And a short circuit is basically when you construct a circuit and the power provided by the battery has no place to go. Okay, there's nothing hooked up to the circuit that's using its energy. Okay, there's no light bulb or cell phone charger or anything like that. And so if we just take wires and attach them together with nothing using up that energy has to be used up inside the battery itself. Okay, which is bad for the battery and also can be dangerous because then the battery can heat up and possibly explode. And that's not good. Okay, so you want to avoid short circuits. But do notice that when I do have a closed conducting path, something happens. Even if it's not good, something happens. And so this is a closed conducting path. Okay, now the final element, besides having a conductor, which these wires are made of conducting materials, and a closed conducting path, which we just saw, you have to have some type of voltage source. And we'll come back to what that means here in just a second. Okay, so on this slide right here, this slide says current and voltage. And it says in an electric circuit, you typically have charged electrons moving around a closed conducting path. This flow of charge is known as electric current. Now, for reasons I don't understand, the symbol for current is not a C, like you might think. Okay, it is actually an I. Okay, it is typically a capital I. So I is the symbol for current. Now again, I don't know why we use I for current, but that's what we use. Now the unit for current, you might have heard people talking about amps. Okay, amps is short for ampere. Okay, ampere was a French scientist who lived hundreds of years ago that we named the unit for current after, just like we name the unit for force, the Newton, after Isaac Newton. Ampere is named for a guy, and so because it's named after a person, we use a capital A for ampere. Okay, so the unit for current is the ampere, and for that we put a capital A. Okay, so if I had, let's say, a current of 2 amperes, I would write I equals 2 with a capital A, 2 amperes. Okay, so that is the most common unit for current. Okay, now current again is basically how quickly those electrons are moving around your closed conducting path. Okay, so we haven't talked about voltage yet, but we will in just a second. But current is basically the rate at which those electrons are moving around your closed conducting path. The symbol is I, and that's measured in amperes. Okay, so pause it here if you need to. Okay, I'm just going to erase this. Now, we're going to use an analogy just to understand the concept of circuits a little bit better. Okay, so what we're about to talk about is just an analogy. But the analogy is this. So imagine water running through a pipe. Okay. The picture on the left, if we look at these two pipes with water running through them, you see the pipe on the left only has a little bit of water trickling out, whereas the pipe on the right has a lot of water trickling out. So if we make an analogy between, water flowing through a pipe and electrical current, remember that in a circuit, it's not water that's flowing, obviously, it's electrons, it's charge. But if we make this analogy, this picture on the left would basically correspond to a small current because we don't have a lot of water flowing in the picture on the left. In the picture on the right, we see a lot of current coming out of the pipe, right? It's just pouring out of there. And so if we make that analogy between water and, electric current, then we would say this picture on the right represents a large current. Okay, so you can think of current as basically how much or how quickly the electrons are moving around in a circuit. Okay, so the analogy, in other words, is we're saying that the water basically represents the electrons. Okay, obviously that is an analogy. There's not water flowing in an electrical circuit. Okay, that's why it's an analogy. Okay, but the water corresponds to the electrons. More water, more current. Okay. So, let's talk about voltage. Now, I said a few minutes ago that the third element you have to have in order to have any electric circuit is a voltage source. Okay, so we're going to talk about what does that mean, voltage. And so in order to understand voltage, we need to understand, okay, so in a circuit you have current, which is basically electrons flowing around. What is it that makes the electrons flow? So in other words, if I'm just going to stick a light bulb on here so I don't have a short circuit. If I look at my simulation and I see these blue electrons moving around in the circuit, they're making the light bulb light up. Then where is that energy coming from? Why is the current flowing around the circuit? What is making the electrons move? Okay, and so this brings up the concept of voltage. And so you can think of current as basically having to do with how quickly are those electrons flowing. Voltage is what makes the current actually flow. Okay, so that's why I said before, in order to force charge to move in a circuit, you have to have what's called a voltage source. Now, voltage, we're not going to get into what voltage is exactly because it's kind of a complicated thing to understand. But voltage is roughly related to electrical potential energy. And so these electrons basically, just like, if you drop a ball and the ball falls down towards the ground, these electrons are basically trying to move from a higher energy to a lower energy level. Okay, and so because of that, they're moving around the circuit trying to get to a lower energy level. Now, the symbol for voltage actually makes way more sense than the symbol for current. The symbol for voltage is a capital V. Okay, now, kind of confusingly, the unit for voltage is the volt, which also has a symbol of a capital V. So for example, if I had a voltage of, let's say, I go to the store and I buy a 9-volt battery. For that battery, I would write V equals 9V, where this V represents the voltage, okay, and then this V represents the unit, which is the volts. Okay, so it's a little confusing because we're using a capital V both for voltage, the symbol, and for volts, the unit for voltage. Okay, so I understand if that's a little confusing. Sorry about that. Now, the analogy we made before was current is basically how quickly the water is flowing around in the circuit. Okay, so I'm going to just erase this and go on to the next slide. The analogy I want to make with voltage is that if you imagine, looking at this picture, we can see that here in the middle we've got 2 water pipes, and we see this pipe on the left right here, where my mouse is wider, and therefore there's more water coming out than this pipe here on the right. Okay, now that means that this pipe on the left right here has more current. However, what makes the water fall down is not, how wide the pipe is, but it's actually gravity. It's actually the height of the water. Okay, and so if current corresponds to how fast the water is coming out, voltage corresponds to basically the height. Okay, because the height gives energy to the water, and the more energy it has, the more voltage there is in this analogy. Okay, so here, if you look at this picture here, this picture on the left corresponds to high current, high voltage. High current because there's a lot of water coming out, and in our analogy, we're replacing the electrons for the water. And high voltage because this height is really high. Okay, so voltage in our water analogy is like the height, the thing that is making the water move to begin with. Okay, so current is the actual charge that's moving and how fast that's happening, and voltage is what is making it move. So in the picture on the right, we can see low current because not a lot of water, but still a lot of height, so this could correspond to high voltage. Okay, so if we do a simple example, using the water analogy, which of the buckets shown has a higher voltage? Okay, we have bucket A and bucket B. So see if you can figure out, just looking at this picture right here, would bucket A or bucket B correspond to a higher voltage if we're using the water analogy? Okay, so it is obviously bucket A, because bucket A is at a higher height, meaning there's more energy causing the water to flow down from bucket A. And we can see, just looking at how much water is flowing, that bucket A would also have a higher current because there's more water here on the left than there is on the right, where it's just like a trickle. Now you might say, well, of course there's more water on the left because, there's more energy, there's more voltage. And it's true that a lot of the time, higher voltage corresponds to higher current. And we'll come back to that in just a second. One more thing I want to say about voltage source. I said this before, but basically as the electrons move around the circuit, the energy from those electrons gets used up in whatever is plugged into that circuit, whether you're charging your phone or it's your TV plugged into the wall or whatever. Okay, now once that energy gets used up inside the device, it has to the electrons have to be pumped back up to a higher energy level, and for that you have to have what's called a voltage source. You have to have something that basically keeps those electrons moving up to a higher energy level so that they can fall back down and use up their energy. Okay, so I'm just going to show you this video clip, part of this video clip right here. So in this analogy, we can see that the red dots represent the electrons, and the voltage is basically like the height here. Okay, and what we see here is that the electrons are moving around the circuit. There's a closed path. Okay, so the electrons are moving around the circuit, and right here is a light bulb. And as the electrons go down, they lose their energy, but that energy gets used up inside the light bulb. Okay, so the light bulb can, light up and provide light to us. Okay, once those electrons fall down and they use up their electrical energy inside the light bulb, guess what? They're useless unless they get some more energy. Where do they get that energy from? The battery. Okay, so the battery is an example of a voltage source, and a voltage source basically acts, you can think of it kind of like a pump, where it just keeps pumping those electrons up to a higher voltage, to a higher energy level. And then once they're up there, they can get used up again. Okay, their energy can get used up again. Sorry, not the electrons can get used up again, but the energy that the electrons have can get used up again. Now, one more thing I want to show you. Notice that there's a switch right here in this video, and when that switch is open, you'll see that in just a second. When that switch is open right here, the electrons can't go anywhere, and so now we don't have a closed conducting path anymore, and so the circuit is going to stop and the light bulb is going to turn off. Okay, and so we said before that one of the key elements for a circuit is to have a closed conducting path. Okay, so this is a switch. This is like the light switch that you have in your houses. When you flip it down, then it basically opens up the path, and if it's not a closed conducting path, then the circuit doesn't work anymore. Okay, and so that is basically what a voltage source does. It basically acts kind of like a pump to keep lifting those electrons up to a higher energy level, and then once they're up at a higher energy level, they can, fall back down and give their energy to like a light bulb or to your cell phone charger, or, your TV, your toaster, your microwave, whatever you have plugged into that circuit. Okay, and then in order to get replenished up to a higher energy level, you have to have that voltage source, either from a battery or from some other type of voltage source. Okay, so that is basically, the very basics of circuitry, talking about the concept of current and the concept of voltage. We're going to go into a lot more detail about some of these things later. This is just kind of, talking about the basics right now. And the last thing I just want to say really quickly is we talked about how a battery is an example of a voltage source. The way a battery works is basically there's chemical energy that gets created inside the battery, and that's where the energy comes from to keep pushing those electrons up to a higher voltage so that they can fall back down to a lower voltage and, give their energy to whatever device you want to power. Okay, so in this video we talked about, what is current? Current has to do with, how quickly the electrons are flowing in a circuit. We talked about voltage, which is basically what makes the electrons move to begin with by, creating a high energy and a low energy, and then the electrons want to fall down to a lower energy on their own. And we talked about the three elements necessary for a circuit to work. You have to have a conductor, you have to have a closed conducting path, and you have to have some type of voltage source that's going to keep giving the electrons energy every time they go around the circuit and replenishing that energy so that the circuit can work. Okay, so that's just kind of the very basics of circuitry. Like I said before, we're going to go into way more detail later on, but I just wanted to kind of give you that foundation. If you have any questions, please let me know, and I will see you in the next video.